Hello and welcome back. Previous video we dealt with addition of whole numbers using the scratch algorithm. Today we'll be looking at the subtraction properties of whole numbers. So the first identity, or the first property for subtraction is the identity subtraction, or known as identity property. So identity subtraction is defined as A, where A minus 0 is equal to 0 minus A. Now you think to yourself, that looks pretty familiar. That's because it is the opposite of A, where A plus 0 is equal to 0 plus A. Do you see the difference? Key hint, our signs. Like I said, this property is for subtraction. This property is for addition. So identity addition, let me make it in this same color. Addition property. Similar to the addition property, but the difference is that it's subtraction, because we're dealing with subtraction. Let's go with an example and see if whether this property holds up. See if it's true or not. Let's do a test. We're going to set A equal to 4. So using the identity subtraction property, 4, where 4 minus 0 is equal to 0 minus 4. Well, 4 minus 0 is just 4. 0 minus 4 is just negative 4. You can say, why is it negative? Why is it a negative 4 and not a positive 4? Well, you see, there is a whole number that is more than 0 behind the subtraction. Whereas this one, a whole number, which is more than 0, is in front of the subtraction. So 4 minus 0, well, that's just 4, right? We know that. We just know. We can't take away 0 from 4. What? Whereas 0 minus 4, we're trying to take away 4 from 0, and 0 is nothing, so really it's just negative 4. That wasn't a very good explanation, now was it? Let's do this. If we have nothing and we're trying to take away, or minus, yes, minus, or take away 4, let's say just 4, that would equal to negative 4. That's what I'm trying to say. Not the greatest, but I hope you understand. Well, let's see. Is 4 the same thing as negative 4? Nope, they are not the same. This 4 is positive and this 4 is negative. Therefore, Therefore, this property is not true. Why? Well, look what I just said. I said that this whole number greater than 0 is behind the negative or the minus, while this side, this whole number greater than 0 is in front of the minus sign. Order matters. How you place the number and where you place the minus sign matters a lot. Order matters. You're gonna box that in to remember. And that's why this property is not true. Because order matter, this 4 is behind the subtraction and we're subtracting it with 0. If it was, I don't know, 5 minus 4, then that'd be 1 and that'd be positive. But since we're subtracting nothing with 4, we get negative 4. Whereas 4 minus 0, we get a positive 4. Orders matters, especially in mathematics. No, not mathematics. In subtraction. Let's move on to the next. Associative property for subtraction. The associative property for subtraction is defined as, parentheses, a minus b minus c, where it's equal to a minus, parentheses, b minus c. Looks familiar to the associative property for addition, doesn't it? Where it was, parentheses, a plus b plus c equals to a plus, parentheses, b plus c. And that's one way to remember of the associative, or these properties with their addition form and their subtraction form. Making little connections. Well then, let's test to see whether this property holds up to be true. Excuse me. Let's set a to be 1, b to be 2, and c to be 3. So we have, parentheses, our a, which is 1, minus our b, which is 2, parentheses, minus our c, which is 3. Excuse me. Which is equal to our a, which was 1, minus our b, which was 2, minus our c, which is 3. We're going to follow PEMDAS. Parentheses first. 1 minus 2. Well, that's negative 1. Negative 2. Numerically wise. 2 is greater than 1. So if you were to do our charge field, we have 2 negatives, 1 positive. We got these 2 neutralized, and we have 1 negative charge left over. That is for here. Minus 3 equals 2. 2 minus 3, same thing. let's do our charge. Our little charge fields. We have 3 negatives, 2 positives. These 2 neutralizes, and these 2 also neutralizes. So we're also left with 1, -1. Do parentheses. -1. Oops. Right there. Well, -1 minus 3, which is -4. Why is it -4? Let's draw our charge field once more. We have 3 negatives and 1 more negative. There is no positives that we can just neutralize or cancel out. We only have 1 additional negative. And how many negative charges are in this field? We got 1, 2, 3, 4. -4 equals to not 0. Be careful, not 0. Why? Well, we have a negative or a minus outside the parentheses. So once we distribute, or let's think of it this way. Here, this is saying the opposite. So the opposite of 1 is -1. Now we have another negative out here. That's essentially saying the opposite of -1 is a +1. So really, this is just 1 plus 1, and that gives me 2. Put down here. Clearly, -4 does not equal 2. Therefore, this is not true. Not true. Why? Well, remember last identity property, we just said order matters. Where you place the minus sign in the numbers matters. Be in front of it or behind it. Oops, too far. So here, it's not true because order matters. Not to say that this entire property, and the same thing with the identity property, not to say that this entire property, well, yeah, no, that one's negative or positive. That one's just not true. Let's see. Yeah, no, that's just not true. That's not true. Order matters. Let's go to the next one. Commutative property, subtraction. The commutative property for subtraction is defined as parentheses A minus B A minus B minus C, which is equal to parentheses C minus B minus A. There you go. That's the definition of the commutative property of subtraction. So let's test this property. We're going to use the same numbers as the last one. A is 1, B is 2, and C is 3. So 1 minus 2 minus 3 is equal to, parentheses, 3 minus 2 minus 1. Let's work it out. Bring that up here. 1 minus 2, well, that's just negative 1, remember? We have 2 negative charges and 1 positive. These 2 neutralizes, and we're left with just one negative charge. Minus 3 equals 2. 3 minus 2, that's just 1, minus 1. What do we get? Negative 4 is equal to 0. Are they really equal to each other? Nope, not at all. So once again, not true. And once more, order matters. And that's it.